The gas law standard is pretty thick. So we've broken it up into this one. We're going to talk about the ideal gas law, the other associated gas laws with the ideal gas law, and kinetic molecular theory. So again, gases are molecules that are spread far apart. They spread out to fit their container, whatever it is. That's why they have an indefinite shape and indefinite volume. And then they have the lowest intermolecular forces when compared to others, because they don't have that definite shape holding them in there. There takes some intermolecular forces to keep that ice cube in a cube. Okay. The kinetic molecular theory says that the gas molecules don't take up extra space. We know they do take up space, but since they're spread out, a lot of other molecules can be interspersed in there. Gas molecules don't have intermolecular forces. As I said, they have low intermolecular forces. So again, we can make the assumption to make our calculations easier that they don't have any. We have the assumption that gas molecules are constantly moving, because until we get down to 0 degrees, they are pretty much going to have some movement. Not 0 degrees, but 0 Kelvin is where we are assuming that motion is 0. So for most of our calculations, we're not at 0 Kelvin. And perfectly elastic. That means when it hits the wall of the container, it's going to come off in an equal and opposite manner, meaning the angle of incidence is equal to the angle of reflection, and is 9. And we have 90 degrees in between there. Now we know that no gases are truly ideal, so they don't perfectly match the kinetic molecular theory. But for the SOL, you can assume all gases are ideal, even water vapor, which was one of the ones furthest from being an ideal gas. Okay, how can we make sure that when we're doing our calculations, we are following that kinetic molecular theory as much as possible? Well, when they are at their gaseous condition, they are closest to ideal. Highest temperature, closest to ideal, because when we look at the scale, cold and hot, as we make things colder, it's going to condense into a liquid. So if we stay as hot as possible, we avoid that. Same with low pressure, high pressure. Low pressure, not a lot of pressure, everything can spread out, gaseous form. As we increase the pressure, again, it's going to condense. So just always think about it as what is going to help it be the most ideal or the closest to an ideal gas when it's at the gaseous. So we have these equations we're going to deal. There's actually 5 equations on this slide. We have the ideal gas law, which is at one set of conditions. So I always say that as 1 in the ideal instead of an ideal, instead of a I. Ideal, 1 set of conditions, 1 pressure, 1 volume, 1 number of moles, 1 gas constant, and 1 temperature. What is the gas constant? It is just a fixed number that helps us relate pressure and volume to moles and temperature. Okay. If you're in kilopascals, the conversion you need is 8.3. If you're in atmospheres, 0.082 is your universal gas constant. There are other gas constants with the different pressures, but those are your 2 main ones. So you're always going to convert your pressure into kilopascals or atmospheres to do the problems. Again, they're not going to give you the formula for the SOL, so do make sure you memorize PV equals nRT and you memorize your 2 gas law constants. All right, gas law triangle is just taking the ideal gas law and breaking it up into pieces. If we're dealing with pressure and volume only, we are all on this side of the triangle, so that's Boyle's law. Boyle's law is when temperature is constant or unchanging. So when this guy is constant, it doesn't need to be on the equation because it's going to be the same on both sides and it would just cancel out. Okay, so that is Boyle's law. Pressure and temperature is Gay-Lussig's law. Volume would be at a constant. We're just going to be comparing pressure and temperature. In this case, pressure is over temperature. So pressure over temperature equals a constant. That's 1 set of conditions on the ideal gas law because I could divide both sides by temperature. Pressure over temperature is going to be equal to a constant when the volume is unchanged, because your volume's unchanged, your number of moles is unchanged, and your gas law constant is unchanged. It's all coming from those problems. Charles's law, when we have V over T and pressure is constant. Now, V over T equals a constant is not going to give you a lot to calculate with, but what that allows us to do is say V over T equals V over T, where V1 over T1 is the starting conditions and V2 over T2 is the ending conditions. V1 over T1 equals V2 over T2. So that is Charles's law in its final form. Gay-Lussac's works the same way. P over T equals P over T. Boyle's law, P times V equals a constant, which is equal to P times V. So we can take out that middleman and just make it PV equals PV. They're on the same line, so they're multiplied. The starting pressure times the starting volume equals the ending pressure times the ending volume. So those are 4 of our laws. Our last one is if pressure, volume, and temperature are all changing, P times V over T equals P times V over T, where the left side are the start conditions, the right side are the ending condition. There is still something constant here. Moles are constant. For the entire gas law triangle, moles are constant because they're not even on the gas law triangle. Okay? For the ideal gas law, only the universal gas constant is constant because it's only one set of conditions. So that ideal gas law is only talking about a specific set, and then things will change as you move on. So if you're trying to figure out which law it is, you got to identify your parts to decide what is going on. A 250 milliliter balloon, milliliters is a volume, is filled with 1.5 moles of hydrogen gas. Moles is represented by an N. Hydrogen gas, Brinkerhoff, H2, at 2 atmospheres. Atmospheres is a pressure. What is the temperature? I only see one volume, I only see one pressure, and I only see one temperature. One ideal set of conditions. So this is our ideal gas law. Now, our pressure is 2 atmospheres. So I'm just going to write 2 atmospheres in its place. My volume is milliliters. My volume for the ideal gas law has to be in liters. So we got to do a little side quest. 250 milliliters over 1, and we're going to go from milliliters to liters. So just write the units in first to make sure your units are canceling, and then fill in the numbers. There's 1,000 milliliters for 1 liter. 0.25 liters. How else can you do it if you're memorizing it? Milliliters to liters is divide by 1,000, right? So our liters is 0.25 liters. Number of moles, 1.5. R, what am I dealing with? Atmosphere. So my R has to be 0.082. It's linked to the pressure. Whatever your pressure is, that determines your R. So your pressure has to be in atmospheres or kilopascals. What is the temperature? That is what we are solving for. And now we're going to switch on. We're just going to go to algebra because we have one unknown for the whole equation, which means it's now solvable. 2 times 0.25 is 0.5 for the left side. 1.5 times 0.082 is 0.123 times t for the right side. We have multiplication, so we got to divide, cancel out those terms. And what we do to one side, we got to do to the other. 0.5 divided by 1.123 gives me a volume of 4.065, so and so on. My volume has to be, or sorry, my volume, that solves for my temperature. Okay, my temperature in gas law is always Kelvin, so 4.065 Kelvin. And then finally, substitute solve sig figs. 2 sig figs there. Important, important, no decimal, not important. Important, important, 2 sig figs. 1 sig fig, I got to round to 1. So I underline the first sig fig. It's in the ones digit, so I'm going to round to the nearest whole number. I'm going to either round down to 4 or round up to 5. This tells me I'm going to round down. My temperature is 4 Kelvin. So if they say, what is the temperature? Look and see what units they have. If they want it in Kelvin, it would be 4. But if they want it in Celsius, you got to do another step because degrees C plus 273 equals Kelvin. So if my Kelvin is 4, degrees C plus 273 equals 4. and that's addition. So I'm going to subtract negative 269 degrees Celsius. So if they ask for it in Celsius, that is where it's going to be. 4 sig figs, when you're addition and subtracting, you're rounding to the least decimal places. So 4 has 0 decimal places, 273 has 0 decimal places. So the answer has 0 decimal places. So don't round that guy to 1 sig fig. Okay, and remember, those are your two R values. All right, which law? 750 milliliters, that's a volume balloon filled with hydrogen monochloride gas at STP. STP, standard temperature and standard pressure. Standard temperature is 0 degrees C. Standard pressure is 1 atmosphere. So when you see STP, don't go, oh, they didn't give me enough information. They did. We have a temperature, we have a pressure, we have a volume. If the pressure is increased to 110 pascals, so we have 2 pressures now, increased to, this is the second pressure, making 1 atmosphere is the first pressure. What is the new volume? Oh, so this first volume is volume 1, the starting volume. This is our ending volume. 2 pressures, 2 volumes. We're going to have the ideal gas law triangle, the gas law triangle from the ideal gas law. We have 1 volume given, 750 milliliters. We have 1 pressure given, 1 atmosphere. We have 1 temperature given, 0 degrees C. We can't leave it like that. We got to always convert to Kelvin by adding 273. So I'm actually going to put an X there so I don't accidentally use it if I need it in the problem. Our pressure was increased to 110,000 pascals. And what is the new volume? And the new volume. All right, so when we look at this, they gave us a temperature, but guess what? There's only 1 temperature, which means the sky is constant. So we can exit out of the equation. We only need Boyle's law here. Pressure times volume equals pressure times volume. Pressure 1 times volume 1 equals pressure 2 times volume 2. What's the rules? The units have to match. So the new volume is going to be in milliliters right now because we started in milliliters. But what about these guys? Those have to change. So when we look at this, there is a whole bunch of standard pressures. 1 atmosphere is the same as a 101.3 kilopascals, which is equivalent to 101,300 pascals. Even though there's a number in between, it doesn't matter. I can grab whichever one I want. 1 atmosphere is equal to 101,300 pascals. So actually, I'm just going to take the 1 atmosphere off of there and change it with pascals since it's the same number. Now I have the same units. Now I can start plugging in. So pressure 1 is 101,300. Volume 1 is 750. Pressure 2, 110,000. Volume 2 is unknown. Math brains on, combine like terms. 101,300 times 750 gives me 75,975,000. And that's equal to 110,000 V2. That's connected by multiplication. So I got to divide. What I do to one side, I got to do to the other. My second volume is equal to 690.6818. Volume, what units? Has to match. I started with milliliters, end with milliliters. Substitute, solve, sig figs, 2 sig figs. Significant, significant. I don't see the decimal, not significant. Significant, significant. I see commas, but no decimals. Not significant, so 2 sig figs. So even though this guy has only 2 sig figs, it's not 11 pascals, it's still 110,000 pascals. All right, so STP, that's an exact number, so I'm not going to use that in figuring out my least sig figs. I'm just going to use the knowns from the problem. So I underline the first 2 significant from the problem. That gives me to my tens. So I'm going to round down to the nearest 10 or round up to the nearest 10. Okay, and this guy is closest to 690. So my answer is 690 milliliters. What if when you looked at the answers, it wanted it in liters? Always check the units they give you. 690 milliliters over 1, we're going from milliliters to liters. This time milliliters is on the bottom because there's 1,000 milliliters in 1 liter. 0.690 liters would be my answer. Why do I keep that last zero on there? Our leading zeros are on the left, never significant. Non-zeros always significant. Trailing on the right, significant if you see the decimal anywhere. I want to keep my, oh, that's 3 sig figs. I only needed 2. So actually, I don't need that. Just need the 2 sig figs for the answer. So 690 milliliters or 0.69 liters would give you your answer. Okay, if students put different temperatures in bottles with balloons on top, then the warmer temperature will have a larger volume because what? I have what? 2 temperatures and 2 volumes. So I could go look at my gas law triangle. 2 temperatures and 2 volumes. So I'm over here on Charles's law side, Charles' law. So they gave this to me in hypothesis form. If students put different temperatures in bottles, that is what the researcher is doing. If IV, so the IV is different temperatures, the warmer temperature will have a larger volume. That is my dependent variable. I'm going to measure the different volumes to see what's happening. Charles's law. This guy, V over T. When the volume went up, the temperature went up. That was my hypothesis, and that is directly proportional. So this is what that graph would look like. Which one goes where? Dry mix. The volume goes on the Y in this case, and the temperature goes on the X, because I was varying the temperature and measuring the change in the balloon or the volume change. That was reacting. Okay, and that's also kinetic energy as well. The more kinetic energy you have, the higher temperature you have.